Hey everyone, today we're going to discuss intermolecular forces to answer the essential question, how do intermolecular forces impact the properties of elements? Alright, so something that comes back is Coulomb's law, remembering the attraction between charged particles depends on the distance between them and the magnitude of the charge. This helps us talk about intermolecular forces because intermolecular forces are forces of attraction between molecules. Inter means between molecules, and forces refers to attractions, that's attractions between molecules. The stronger the intermolecular forces, sometimes called IMFs, the more strongly molecules will attract to each other like magnets. Right? London dispersion forces are a random, weak, and temporary attraction between atoms and molecules due to uneven dispersion, also called spread of electrons. The dipole-dipole force is a medium strength attraction between only polar molecules, not nonpolar molecules, due to the oppositely charged poles. And then hydrogen bonds is a special type of dipole-dipole force that's very strong. It's our strongest intermolecular force, and it's attraction between extremely polar molecules. A strong partial positive hydrogen on one molecule is attracted to a strong partial negative on another molecule. And this only happens when hydrogen is bonded to the elements fluorine, oxygen, or nitrogen. All right, so what we're going to start with here is London dispersion forces. These are random, temporary attractions between atoms and molecules due to uneven dispersion or spread of electrons. All atoms and molecules have London dispersion forces. Every single one. What we find is the larger the atom or molecule, the stronger the London dispersion forces become. The whole thing that happens with London dispersion forces is that sometimes electrons will temporarily gather on one side of an atom or molecule, making very weak partial charges. So neon here with its 10 electrons, if we take a snapshot in time, its electrons have gathered on this side of the atom randomly, all right? They've spread out randomly and they've just ended up that way. If another neon atom is nearby, its electrons will be attracted to this partial positive charge arising here, and it will also get this very slight pull. Immediately afterwards, because this is a temporary attraction, they go back to the way that they were and their electrons keep going about. That's why this is random and temporary. Electrons are moving about. Sometimes they just happen to end up on one side of an atom, tipping it more towards positive or negative charge, and that results in temporary attractions to other atoms. If we're talking about a larger atom, this time argon, which has 18 electrons, and it has another energy level compared to neon, there's a lot more space for the electrons to disperse. What that means for us is that it is more likely that we'll end up with a situation where electrons are dispersed unevenly because there's more space and more electrons moving around. And in this case, argon can have a lot of electrons end up tipping a little bit on this side towards a negative and tipping a little bit on this side towards a positive. And other argon atoms nearby, or any atoms nearby, will also feel this slight attraction. In this case, this is a stronger attraction because there are more electrons being gathered on one side, so the charges are a little bit bigger. So argon feels a slightly stronger attraction to other argon atoms than neon does to other neon atoms. Right? And then again, because this is random and temporary, the electrons keep moving. When the electrons keep moving, they do their thing, and those partial charges disappear. Okay? So they're random, temporary attractions. Now, if we're going to discuss some specific examples, right? Fluorine, chlorine, bromine, and iodine all make one bond to each other to make these four molecules, F2, Cl2, Br2, and I2. Now, the thing with London dispersion forces, all right, the larger it is, the stronger the LDFs, as we just talked about. Now, the best thing to use is atomic radius to determine which is larger, but molar mass is also an okay approximation of London dispersion forces. So the larger the molar mass, the larger we would expect our London dispersion forces. Fluorine is 38 grams per mole. Each fluorine is about 19 grams per mole. Chlorine each is about 35 grams per mole, so we get about 70 overall here. Bromine is each about 80 grams per mole, so we get 160-ish grams per mole as our molar mass, and iodine is about 254. So as we continue to get larger and larger molecules, we get more and more London dispersion forces because there's more area for those electrons to disperse. All right, so here is the real-world example of that. Okay, so these intermolecular forces, again, are forces of attraction between molecules. The stronger the intermolecular forces, the more molecules will attract to each other. If the attraction is really strong, the molecules condense into a liquid, and if they're really, really strong, they actually stick together into a solid state. All right. So F2 and Cl2 are gases because they're smaller molecules. They have less space for their electrons to disperse. Their London dispersion forces are weaker, and so they don't attract to each other as much and stay as gases. But bromine and iodine have much stronger London dispersion forces, so these molecules actually stick to each other decently strongly. These random temporary partial charges from the London dispersion force causes them to stick to each other like magnets. Right? Iodine's being particularly strong, so it's actually a solid at room temperature. Okay? All right, so the next force we're going to talk about is the dipole-dipole force, and this is an attraction, again, as all intermolecular forces are, this time between polar molecules, only polar molecules, due to oppositely charged poles, positive and negative. So again, all polar molecules will have the dipole-dipole force. Non-polar molecules will not have any dipole-dipole force. The more polar a molecule is, the stronger the dipole-dipole force will be. So, in order to take a look at dipole-dipole forces, I've brought 4 polar molecules to look at. All right. We can check to see if they're polar by taking a look at their electronegativity difference. So remember, we take one electronegativity minus the other electronegativity in the bond to find the difference. Okay. So these are all pretty solidly polar. All right. Hydroiodic acid is a little close to the range of nonpolar, but otherwise they all have dipoles, partial positives and partial negatives. So if we're to show them on the scale here, hydroiodic acid is just barely polar, hydrobromic acid is a little more polar, hydrochloric acid is more polar still, and hydrofluoric acid is so polar it's almost ionic. The electrons are almost being transferred instead of shared. If we move forward here, okay, and I've also gone ahead and I've used a software to calculate the charges of these and represent it with colors. All right. So this dipole-dipole force, again, is an attraction between polar molecules due to oppositely charged poles. So like this partial negative on iodine can attract to a partial positive on a different molecule, or this partial positive on hydrogen in this molecule can attract to the partial negative of any of these other molecules. Now what we notice here, okay, in this representation, is hydrofluoric acid has this really dark blue and this really dark red because it has very large partial negative and very large partial positive charges due to this big difference in electronegativity. Hydrochloric acid, significantly less difference in electronegativity, so the colors represented here kind of reflect that the charges are not as big. And as we keep going, these partial charges are getting smaller and smaller as our molecules get less and less polar. All right? So this also does connect back to Coulomb's law. The attraction between charged particles depends on distance and magnitude. Since hydrofluoric acid has a much, much higher magnitude of charges, hydrofluoric acid experiences a very strong attraction to other hydrofluoric acid molecules, and they'll stick together like magnets. Something like hydroiodic acid here has much less partial negative and partial positive charges. The magnitude, the strength is much lower. So these molecules feel very little attraction to each other. Okay? So with a lower magnitude of charge on its poles, because the electronegativity difference is very small, the attractions between hydroiodic molecules are weaker. They don't stick to each other as much. The intermolecular force is weaker. Since hydrofluoric acid has a higher magnitude of charge on its poles due to its greater difference in electronegativity, much larger difference, the attractions between HF molecules are stronger. That intermolecular force is much stronger. All right, so getting back to the point of intermolecular forces being forces of attraction between molecules, knowing that the stronger intermolecular forces lead to stronger attractions between molecules, here are our 4 molecules from the last couple slides. What we notice is hydrofluoric acid with its very strong partial charges is actually a liquid at room temperature, whereas hydrochloric, hydrobromic, and hydroiodic have much weaker dipole-dipole forces, and their molecules don't attract to each other as much, meaning that they stay as gases. They don't have enough attraction to each other to stick together as a liquid or to bind together as a solid. So this is what we end up finding here, and it directly relates to the strength of their intermolecular forces. Okay. These dipoles are permanent though, because the electronegativity difference, they always have this difference in charge between these two atoms here. So hydroiodic acid, being the least polar, has the weakest dipoles, least attraction to its other molecules. Hydrobromic is a little stronger, hydrochloric is a little stronger, but hydrofluoric is the strongest because it has the most polar bond, the greatest difference in electronegativity, so it has the strongest dipoles, the strongest partial positive, partial negative charges, the greatest magnitude, which according to Coulomb's law means the greatest attraction for other molecules. So what we find is the weakest dipoles have a small electronegativity difference. They have a low magnitude of charge. Really strong dipoles have a large electronegativity difference and have a higher magnitude of charge. And now we get to the last type of intermolecular force. Hydrogen bond is actually just a special type of dipole-dipole force. It's a very, very strong dipole-dipole force between extremely polar molecules, one of which you've actually already seen. HF, this is considered as having dipole-dipole forces, but this is also a very, very strong dipole-dipole force, so strong that it's got a separate name called hydrogen bonds. This happens when a very strong partial positive on hydrogen can be attracted to a very strong partial negative on another molecule. And this only happens when hydrogen makes an extremely polar bond to fluorine, oxygen, or nitrogen. If hydrogen is bonded to a nitrogen, hydrogen bonds are possible. If hydrogen is bonded to fluorine, hydrogen bonds are possible. If hydrogen is bonded to oxygen, hydrogen bonds are possible. We represent these with these dashed lines. So, for example, this hydrogen here, which is a strong partial positive, can be attracted to this oxygen here, which is a strong partial negative charge. Or this partial positive on this hydrogen can be attracted to the partial negative on this fluorine. Okay? So we have these hydrogen bonds as a very, very strong attraction between molecules because it's very, very polar. So polar that it gets its special own name. So I'm going to show you some more complicated molecules, which you've actually heard of before: adenine, thymine, guanine, and cytosine. If we notice here, here's a nitrogen attached to a hydrogen. Here's a nitrogen attached to a hydrogen. All right? So what we find is, all right, these can make these hydrogen bonds. And here's a hydrogen attached to a nitrogen, hydrogen attached to nitrogen, hydrogen attached to nitrogen. That's one of our F, O, or N elements. So we get these hydrogen bonds between these different nitrogenous bases, all right? And maybe you've guessed it if you remember your biology. But hydrogen bonds are what hold your DNA together. Without hydrogen bonds, your DNA would not be one molecule. It would split apart at room temperature, and it would get mutated, and you would probably die and never have kids, right? So hydrogen bonds, pretty cool, hold together things like DNA and water and all this cool stuff. Okay, so this is the most valuable summary I can leave you with. If we want to compare the IMF strength of two molecules, we can use the following ideas. LDFs are the weakest intermolecular force. All molecules have them, but larger molecules have stronger LDFs. Dipole-dipole forces are medium strength. Only polar molecules have dipole-dipole forces, but the greater the difference in electronegativity, the stronger the dipole force. And then hydrogen bonds are the strongest overall. So this only happens, though, with polar molecules bond with an HF bond, an HN bond, or an HO bond. If one molecule has more forces than the other, it's got stronger intermolecular forces. If they have the same forces, you can either compare LDFs or compare the dipole-dipole force. Larger molecules are stronger, or the greater the difference in electronegativity, the stronger. Those are the two you can go with.